Hello, welcome to a presentation explaining question 18 from the January 2010 Edexcel Physics on the Go exam paper. Okay, pause the video and read this question. Okay, so this question is talking about a kind of demonstration you can do which involves getting a ruler, balancing it on the edge of a table like this, putting your finger here so it acts as a pivot, popping a coin there, putting a coin in front of the ruler here, and then hopefully you can see from this diagram and from this diagram the guy's going to give it a good smack in that direction, and what's intended to happen is that coin A will fall directly down and simultaneously coin B will be flung, follow a parabolic curve and hit the ground at a practically identical moment in time. Obviously in this diagram the ruler is thicker than a real ruler, so it doesn't really give you a fair idea of exactly how things are going to happen. Right, so the question is asking us to use Newton's first law to explain why coin A has no horizontal motion. Okay, well, Newton's first law states that a body at rest will remain at rest and a body in motion will remain in motion. So coin A is at rest and will remain so unless acted on. Just scribble that. Will remain so unless acted upon by an outside force. Okay, full stop. Since the ruler is very smooth, so brackets low friction, this does not happen. Okay, and that should be sufficient to get both marks for that question. Okay, let's have a look at the next question. Okay, pause the video and attempt the question. Okay, so the fact that both coins, one fell perfectly vertically downwards and one fell following a parabola, yet they both strike the ground at exactly the same time, having been dropped or struck at the same time, so been left to free fall at the same time, means that their vertical acceleration must have been identical. The fact that their vertical acceleration was identical, despite one of them having horizontal velocity, shows that horizontal and vertical motion are separate. So this is just that summarized. Okay, both have identical vertical acceleration, despite the fact that one coin is moving horizontally. This is enough to get you the mark. Okay, pause the video and read this question. Okay, there's lots and lots of different ways of answering this question. Okay, you could use a Suva equation. You could use v squared is equal to u squared plus 2as. The initial velocity would be 0, so it would just be v squared is equal to 2as. You could probably get it off a velocity time graph. The velocity would start at 0. Well, you definitely could get it off a velocity time graph. You could know that this would be 0.85. You could know that the gradient here would be 9.81, and with some clever manipulation you could probably find the maximum velocity. You could, probably the easiest and simplest one to do is just to use energy and equate potential energy with kinetic energy. Whatever potential energy, mgh, potential energy, you have at the start will be equal to the kinetic energy you have at the end. So the mass won't change. You can divide both sides by mass, cancelling out mass. Get rid of the half here by multiplying both sides by 2, so you get 2gh is equal to v squared. Do the root of both sides, gets you to just v. Substituting the numbers into this gives us 2 times 9.81 multiplied by the height, which was 0.85. Okay, as I said here, the height, the area under this little section of the graph would be 0.85 as well. So 0.85. Putting these numbers into the calculator gives us 4.083. So you could round that up to 4.1 meters per second. Again, that is close enough to that we'd be happy with the answer. Okay, now it says after 0.42 seconds, the second coin lands at a horizontal distance of 1.1 meters from the table. Calculate the velocity at which the coin strikes the ground. Right, so you might be tempted to say, oh, it's going to be the same velocity as that. Well, actually, one coin, the first coin we're talking about here, fell directly downwards. So if you was to look at, as it hit the ground, if you was to draw a picture of its instantaneous velocity at that moment, it would be an arrow with a length suitable, or to scale with its velocity. If we were to look at the other coin, which went and followed this parabolic curve, it's going to strike the ground at an angle. Let's put the ground in. Its velocity on impact is going to be slightly different. It's going to be at an angle, and it's going to be made up of the horizontal component and the vertical component of velocity. So you've got the vertical component there and the horizontal component there. Okay, probably a little bit messy there. Hopefully I'll make it a bit clearer here. So let's work out firstly what the horizontal component of the velocity was. We've been told that the coin went 1.1 meters from the table, so from this distance was 1.1 meters, and it took 0.42 seconds. So I can just simply find out for the horizontal. I can find out the velocity by doing v is equal to distance divided by time, or sorry, displacement divided by time. 1.1 meters divided by the time, 0.42 seconds. Okay, calculating this gives me, let's get the calculator, 2.619 meters per second. Okay, so we can just round that up to, or round it down to 2.6 meters per second. Okay, so now let's, well, we know the vertical components. We don't have to do any calculation. Vertical is just equal to 4.1 meters per second. Okay, so I want to just recreate this little diagram over here. I just did this as a quick sort of explanation. So we've got a vertical component of velocity we know. Try and draw it to roughly scale. 4.1 meters per second. We've got a horizontal component, which we also know now. Try and draw it to scale again, 2.6. Okay, and we can find the sum of these two by taking this vector and putting it tail to tip on the end of this vector. So the easiest way of doing that is creating a little guiding lines to help us. So the sum is this dotted line here. Okay, and that's what we want to find the magnitude of anyway to start with. So the easiest way probably is to use Pythagoras, just to find the size of the hypotenuse here. So you can say a squared plus b squared is equal to c squared, c being the hypotenuse. So we've got 4.1 squared plus 2.6 squared should be equal to c, and take the root of all of that, so I've done the root of both sides again. And calculating that gives me 4.85 meters per second. So I'll put the answer in here, 4.85 meters per second. And then the angle, and I had to redo this video because I did it too quickly, the angle of the velocity to the horizontal. Okay, so we're looking for this angle here. Okay, so I'm just going to label up the triangle because I'll be using trigonometry. So this is the hypotenuse. This is the opposite of the angle, so it's the opposite. This is the adjacent. Okay, so I'm going to do my standard SO, CAR, TOA. Okay, I'm going to be using, well, I can use the opposite and the adjacent to find the angle. Okay, so I can use tan. Tan theta is equal to opposite over adjacent, 4.1. The adjacent here is going to be 2.6 as well, 2.6. Okay, and calculating that and then taking the inverse of tan of the answer will give me an angle of, so on your calculator you have to press shift tan and then whatever this answer was, put it in, and you'll get 57.8 619 degrees. So we can just round that up to 58 degrees. Okay, I hope you found this useful. If you have any questions, please post them in the comments. Thanks for watching.